We've already talked about the background or the basis for finite element analysis, and we walked through the essential components of it. And I also gave you a very brief example using a straight bar with SolidWorks and then again with ANSYS. So I want to look at those more closely because you'll recall that I did a quick hand calculation, and with the bar example that I used, my hand calculation gave an expected deflection, so total stretching of an axial load of 9.52 microns. Now, doesn't seem like much over a 200 millimeter bar, but it's a number that has been the sort of calculation that engineers have trusted for a very long time. We don't have necessarily at this point the ability to actually do the experiment of a part that we want to manufacture and test it and measure its deflection to see what it really is. So we have to rely on something. And a tried and true trusted analysis method such as what I described is a good starting point. So if we're going to use a simulation, we can use that hand calculation as a reference check. Did we actually replicate that number? Now, um, looking at the CAD model, the model that I started with was this one with a fixed end constraint here on the top end and a force here on the bottom end of 1,000 newtons. And when we meshed it, and we meshed it with a variety of different sizes, we got a number of different results. None of them were 9.52. This example that we're looking at right now was with a mesh size, let me just pull that up, a mesh size of 2 millimeters. And so if I create that mesh, you recall that it was a mesh size about like so. And that's fairly fine. Those are a bunch of tetrahedrons in this structure. And with all the data points there, knowing that this solution was achieved by doing a matrix inversion of whatever number of element points we have in the model, that took quite a bit of computational time, and we would like that answer to be correct, especially given that we've just spent some computer horsepower in doing that. So we need to look at the model more carefully and see if our numbers were correct. Here's a plot of my results where the horizontal axis here is the grid mesh size. So I started off with a very coarse mesh of 10 millimeters on a side. That's the whole width of the bar. And I did a simulation of that. And then I made progressively finer and finer mesh points up to my smallest, because of limitations in the model, the computer horsepower I had, was 1 millimeter. So I went from basically a factor of 1,000 in terms of number of solution points. And my 10 millimeter grid gave me a deflection that it predicted total deflection of 9.5 microns. And you can see that as I made the mesh finer, I got a different answer. And maybe I stabilized at 9.12, sorry, 9.512 millimeters. Whereas this point, 9.52, was my expected. So clearly, the model that I created was being deflected less than I anticipated. So here we are back in SolidWorks, and this is one of the model runs that I did to generate that plot of the deflection. And you can see this is a 2 millimeter grid size. And if I look at the stresses, you'll recall from the previous video that I had set the constraints such that this top end was fixed. Now, you notice here uh, that there's a high stress area showing up in the corner, and rather oddly, it seems to be magically shaped like the mesh. And if you look at the mesh there, you can see that the shape of the strain looks sort of triangular and sort of scaled with that mesh. If I go and I look at rerunning this, and instead of a 2 millimeter mesh, I have a 7.5 millimeter mesh. You can see that I've got a bigger grid, and you'll see that again, there's these artifacts from the mesh size. So one of the problems of this this model is that it's very sensitive to the size of the mesh that I'm using in the model. However, looking again at my plot of data, where I changed the mesh size and it improved things, I got finer and finer mesh, and my numbers seem to be consistent everywhere from 3 millimeter mesh and smaller. But they didn't come out to be what I expected. What I expected was 9.52 millimeters. So a study like this, when you're looking at your finite element model and your solution, allows you to first of all say, what's the effect of the coarseness of my grid, and do I have a fine enough grid to represent the features that I'm trying to model? In this case, clearly it looks like I need to have a 3 millimeter grid or so, and then I can be somewhat trusting of the result. But there's another feature here as well that's kind of curious, and that is, what's all this going on? The fact that my bar necks down at the fixed end, that wasn't what I was expecting. At least that wasn't included in anything to do with my simple hand calculation. And if I'm trying to compare my reference, which was a hand calculation, to this model, then it looks like maybe I've not got the same geometry. So we've talked about mesh size, and now what I'm going to have you consider is the boundary conditions. So on one boundary condition, we're using a force, and that force is normal to the surface. So there's no other constraint other than essentially a natural boundary condition. And yet, I've applied this essential boundary condition of a fixed support here, and that's forcing this rectangle to stay fixed, stay rigid. If we were to measure the dimension from this point, I'm not sure if we can still do that. Yeah, from this point to this point, measure, pick that vertex to there, it's still exactly 10 millimeters. So we forced that end of this bar to stay rigidly 10 millimeters by 10 millimeters. We've put an extra constraint on it that, at least in my simple model of PL over EA, wasn't really what I was considering as part of the model. So what I've done is, instead of using a fixed constraint for the fixture, I've applied two rollers. So one roller slider constraint, which is on this top face, and that is essentially a planar set of rollers. Imagine it an ice sheet. So the top of this plate is glued to a sheet of ice, but it can slide around sideways. So that's one constraint. If I try to model it with just that, then I'll get some errors, because essentially the model is saying I don't know where it's going side to side. So I've added to that two more slider constraints, which would be on the opposite faces. Now these would be essentially holding this plane and this plane fixed in space, at least aligned, so that they can't move in either direction. So what I've done is I've changed the constraints on one end. I've kept everything else the same. If I mesh this this body, let's say I'll use the 2 millimeters that I've done in the previous example. So I've got the same size mesh that that we were talking about a moment ago, and if I run this study, nothing else has changed other than my constraints, and the end of it, we don't see those strange effects. In fact, the only effects we see from the grid are it looks like noise essentially in the coloring. But in general, everything looks pretty consistent. There's some strange features in here, but on average, it looks fairly boring, which is in some sense good. If I look at the total deflection, my total deflection here is 9.52552 microns. That's a lot closer to the simple calculation that I've done. Comparing that result, you can see here, I looked at doing the original model with a progressively finer and finer grid here, up to 1 millimeter spacing from 10, and there was a pretty big change in the total deflection that I predicted. However, neither of those methods gave me the 9.52 that I expected. So if I change the boundary conditions, i.e. the way that I was fixing the end of this bar that was attached to the ground, I get two things. One is I'm closer in general to the 9.52 that I predicted with my hand calculation, and there's almost no effect from the grid size. So both of these things are tools or techniques that you need to use when you're doing finite element analysis. You need to look at varying the grid size with a couple of ranges to see how that changes your result, because it might. If you don't have the grid the right size, you're not going to recognize the features. And you also have to remember that this model solution you're creating is fundamentally dependent upon boundary conditions. So if the boundary conditions are not appropriate for what you're modeling, then maybe in fact what you're solving is a different problem. This blue line here is essentially a different problem than I thought we were solving with a simple straight bar that is essentially simply supported on one end. And this orange line, which was from my second version of the supports, is more realistic compared to what I was expecting, and because I didn't inadvertently create some small feature because of the end constraint that I didn't know I was going to be modeling, the grid was much less sensitive to changes because there were no artifacts of that small scale that the grid couldn't represent. So this is an opportunity for you to stop and think about when you're doing the models. You need to think about the boundary conditions very carefully to make sure that you really are modeling what you think you're modeling. And you need to look at the meshing very seriously. Both of those things are absolutely critical in making sure that the quality of your results, the quality of your model is as good as it can be. So I'll stop there with this video. We'll move on in the next video to look more at some detailed features and how that affects your simulation. So in the meantime, please take time yourself and try to make a really simple model of something, not a bar. Try a straight rod. Um, so a circular cross-section rod, similar to what I've done, and see if you can reproduce a similar result to what you would do by hand calculations. Simple hand calculation, PL over EA, double check to see that the material properties you're using in the SolidWorks CAD are the same as the material properties you do by hand calculation, and give it a try and see how close your simulation can come to your hand calculation. And we'll talk again. Thanks.